Hello, and let me welcome you to this webinar. My name is Daniel Sturm. I'm the current president of the Urban Economics Association. I'd like to welcome you to the 2020 lectures on urban economics. If you could look around our virtual meeting room, you would see several thousand, about 2,000 others who are interested in urban questions. If you needed further proof that urban economics is important, here it is. You can see on the UEA website that in addition to this set of 8 lectures, we will run further online events later this year. I also hope to see you all in person at future UEA conferences. Let me say a couple of thank yous before we start. First, we are extremely grateful to our 8 distinguished economists for agreeing to contribute to this series. Second, we are also very grateful to the International Economics section at Princeton University, who've provided us with an XXL-sized Zoom webinar license, which is not cheap. Finally, I'd like to thank Claire Balboni, Fabian Eckert, Kurt Schmidt-Heine, Matt Turner, and Don Davis for helping to organize these lectures.
So the lecture will run from 11 a.m. until 1 p.m. Eastern Time. There'll be a short break at the midpoint of the lecture. And should you wish to follow your own slides, there are a set of the slides used for this lecture available now on the UEA website. So with that, I'll hand over to Ed. Thank you very much indeed, and we very much look forward to your lecture.
Thank you, Claire, and thank you all for coming today. This is a great honor for me, and I'm really delighted that you've let me into your homes, and I'm excited to be trying to teach you a bit about urban economics. We're going to be doing two canonical urban models today. But before we get to this, I wanted to start with an overview of the field of urban economics. And Daniel really said it. This is an incredibly exciting time for the field for many, many reasons. The coming together of empirical skills, structural empirical work coming together with advances in theory, the ability to use big data to measure changes over space. And of course, we are in a moment in this COVID-19 pandemic in which we have all chosen to de-urbanize, or many of us have, in a radical way. And so the diseconomies of agglomeration have come particularly to the fore right now. Now, what is urban economics? Above all, it's the study of the location of economic activity over space. So that's more properly economic geography, but it's subsumed as part of urban economics, because at the heart of urban economics is the question of why cities? Why do people come together? Cities at their heart are the absence of physical space between people and firms. Cities are density, proximity, closeness, and they represent a choice. Since proximity is fundamentally about reduction of transportation costs for goods, for people, and for ideas, transportation economics is a closely related field. I would say the second question, and you should be able to see why these two questions are so related, is how does location impact economic activity? How does being amidst a maelstrom of human beings in a big city make us more productive if it does? And that's what the economics of agglomeration is about. How does being present to smart people make us smarter, help us to learn more quickly? And that's what human capital externalities are about. And there's a whole range of fields of topics on spillovers, on neighborhood effects, on how the impact of the company you keep how the impact of the company that you keep impacts who you become as a human being. Churchill famously said, first we build our buildings and then they build us, or first we shape our buildings and then they shape us. And I think embedded in this question is the idea that our physical space, and particularly the humans who occupy that space, determines a major part of our experience in life. And then the last question is, what determines the price that people are willing to pay for in particular places? And that's why real estate economics is a close cousin of urban economics. Because ultimately this question of people's willingness to pay for things is intimately related to how economists view space. There's a great quote of Robert Lucas, which is supposed to be evidence for agglomeration economics, is the fact that what are all those people in downtown New York or Hong Kong or Chicago paying for if not for the ability to be close to other businesses? All right, now let's just start with some motivating pictures. So this is the population of the United States. These show density levels across the United States. And as you can see, we are looking at anything but a uniform plane of people, right? There are parts of the United States, and it is a vast country, which are very densely populated, the Eastern Seaboard, the geographic clusters around San Francisco and Los Angeles, the tip of Florida, Chicago, Detroit. And then there are huge tracts of land, huge areas which are uninhabited. Now, this plain at one point in time had geography that really mattered, right? If you look at all of the 20 oldest cities in the US, 20 largest cities in the US in 1900, they were on major waterways in 1900, from New York and Boston, the oldest, typically where the river meets the sea, to Minneapolis, the northernmost navigable point on the Mississippi River. But over the course of the 20th century, transportation costs plummeted. Proximity to those waterways became less important. And so geography was less likely to determine things, at least those transportation cost related geographies. We'll get back to later whether or not the issue of just the consumer side of geography, just pleasant climates drive where people locate. But there's no geography that can explain why 20 million people live in one large agglomeration and leave vast parts of America much more empty. So that's a fundamental question of our discipline. Why is it that people locate in the way that they do? And then why is it that incomes go along with the density? So this is a map of average household income in the US. And as you can see, the denser portions that were shown on the previous map are also the ones where people were paid the most. And this can be interpreted as reflecting the fact that some areas are innately more productive and bring people to cities. That's actually the only explanation that we're really going to consider when we get to our model of location across space today. But of course, the whole field of urban is, believes in something like agglomeration economies, the fact that we become more productive by being around other people. And so some part of this relationship between density and income reflects the density itself having a causal impact on income. This is another way of seeing this. So this takes the 3,000 odd counties in the United States and it splits them into tenths. Each one of those dots represents 300 counties, 1/10. The lower line shows the relationship between density and earnings. The top 10th of America's counties by density have earnings that are 50% higher than the least dense half. And then the higher line shows the reshuffling of America, the movement of people to higher density areas. The fact that at the start of the 19th century, Americans may have been leaving their dense enclaves on the eastern seaboard to populate the empty spaces between the oceans. But at the start of the 21st century, instead of spreading out, we are clustering in. This is the relationship between price growth over the past 20 years or so and density. So again, you see sort of large price growth in the densest fifth of America's metropolitan areas and no price growth in the bottom fifth. I'm saying this not because this is in any sense going to be an empirical lecture. It is not, but these are the types of facts that motivate us to walk through these models. These are the sort of questions that we want to be able to answer, not just why are prices different at a point in time, but why are they rising? Can we understand why some cities grow and others don't? These models are meant to organize our thinking about this. And of course, there's COVID-19. Now, we've talked about I mentioned the agglomeration effects, the benefits of density, the fact that if two people are close enough, they could cooperate, they can buy and sell from one another. But if two people are close enough to share an idea in the same room, they're also close enough to share a contagious disease. And right now we are in this massive global exercise of functionally de-urbanizing our world in response to contagion. Now, we have lived through a blessed century. The past 100 years has been one in which the cities of the West have been remarkably free of killing pandemics, AIDS being the one exception, but because that was primarily a sexually transmitted disease, it felt like less of an existential threat to cities than diseases that are spread by more casual human contact. But throughout most of history, from the plague that hit Athens in 430 BC to the start of the Black Death in Europe, which came in the form of the Justinian's plague in Constantinople in the 530s, and probably stopped Justinian's attempt to rebuild the Pax Romana in the Mediterranean world, we have had contagious disease be a running companion of cities. A boy born in New York City in 1900 could live about 7 years less than a boy born in rural America in the same year. And it was roughly the same life expectancy gap that existed between Shakespeare's London and the rest of England. Now, as part of this, great exercise in de-urbanizing, there's a question as to whether or not we are going to sort of fundamentally reshape our world around remote working. Will this shift to doing everything by Zoom not just be a temporary aberration, but be permanent? That is also a question of urban economics. So here I'm taking this very nice measure of Jonathan Dingle and Nyman of the predicted ability to work remotely This was all pre-COVID, and I'm showing some of my data, which comes from an alignable survey of small firms, showing that in fact they got it right. So kudos to Jonathan Dingle and Nyman. They're actually predicting which areas are remote working, and so they really are able to predict it. But I should remind you that the bulk of urban employment in the 21st century is in various services, and many of those services have been the one safe haven for workers who were outsourced to lower wage countries or replaced by machines. And this ability to sort of serve coffee with a smile and have someone pay a premium for it has been the one sort of protective thing that less skilled people can do, whether they're in London or in San Francisco. If all of a sudden having a human being serve you a coffee is a source of fear rather than a source of pleasure, then what happens to the 32 million Americans who work in leisure, hospitality, and retail trade? And that, again, is fundamentally an urban question. So, down to business. The two models are the Alonzo Muth Mills model, or hereafter AMM model, which is a model about the location of people within a city. It characterizes a spatial equilibrium, which is organized around a single central working spot. It's going to hold wages constant. We're going to be focused on the simplest version of this, in which everyone earns the same wage, everyone faces the same commuting costs, and it's going to be explicitly spatial in the sense that all locations are indexed by this one geographic variable, which is proximity to a downtown where everyone works. And so you should think about organizing your thoughts. You should think about a featureless plane of which there's a giant skyscraper in the center, and everyone in the city is commuting to that skyscraper, effectively walking, at least at first. This emerged in 1962, and it has been sort of the hallmark of spatial models forever. It's sort of the first widely popular introduction of the spatial equilibrium. The Rosen-Roback model first emerged in 1979, and it's a characterization of the spatial equilibrium across cities. Whereas it seems reasonable to assume that wages are not a function of where you choose to locate within a city. So people may in fact have different wages within a city, but it's typically not, those are not typically determined by where they choose to sleep at night. Certainly which metropolitan area you choose to live in is in fact going to determine your wages, right? There are very substantial differences, and we just saw them between high wage metropolitan areas like San Francisco and low wage metropolitan areas like, for example, Brownsville, Texas. The Rosen-Roback model is going to treat this. It's going to treat wages as endogenous, but only insofar as a higher amount of labor in a city is going to move you along the labor demand curve. It's not going to explain why productivity differs across space. And models, this work predated the sort of models of endogenous agglomeration economies that really start with Krugman in 1992, and which will be modeled in a later lecture. It's far less explicitly spatial than Alonzo Muth Mills. So Alonzo Muth Mills is really about a circle or even a straight line, a straight linear city. Rosen-Roback, you just have these metropolitan areas that are plopped down in different parts of the country, and they're not really speaking to each other. You're just choosing which one to locate within. And so it's far less explicitly spatial. Okay, just to motivate ourselves, I'll show you a couple of graphs of cities. And we're moving on to the Alonzo Muth Mills model. And so this is density within Boston. So Boston is organized around an ancient port. It has a central business district, which is sort of the core area. And the population is densest near those areas. It then falls off with distance, and it falls off fairly radically. And you can see this in this map. So the population is steep in the center, density is steep in the center, and then it's flat further on. This shows the average commutes, which ideally average commutes would show that it was longer to get into the city farther away. That's what we're going to be assuming. But interestingly, that's not totally what we're seeing here. We do see some areas in the very center of the city where commute times are quite low, but then there are some far away areas like the one in the top of the map where commute times are low. And of course, there are pockets of low, high commutes, which are the red ones, which are followed further away by pockets of green. That's to remind us that the world is somewhat more complicated, and there are multiple things going on here. Often when you see the red areas that are fairly close in, those involve public transportation commutes that are fairly lengthy. And the green areas that are closer in are typically car commutes, which are much shorter. So the average commute by car in the US is 24 minutes. The average commute by public transportation is 48 minutes. And you probably want to think about public transportation involving a time fixed cost that you have to pay no matter how long you take the subway for, of between 15 to 20 minutes. So that's why some of these commutes that are closer in are longer. And the green areas that are further out represent different employment centers. So the ones in the north are the ones in the Merrimack River, Lowell and Lawrence, where people are actually working there. And then getting into Worcester as you get a little bit further out on the west side of it. So things are slightly more complicated, but there's at least some supportive evidence that the green tends to be closer in than the red. And this is, of course, median housing value. And what you're supposed to be seeing is the higher values are closer to the city center. There's a bit of that. It's become actually more true over time in Boston, but there are, relatively lower cost areas that are at the city center and higher cost areas that are further out. And that also reminds us that the world of housing values is complicated. What we're not particularly, this is straight census data. We're not controlling for the quality of the house. We're not controlling for the quality of the school district. And all of those will interfere with our model. Let me show you Manhattan. So this is the closest you come to a true linear city. It's just a long, narrow city with two central business districts. The light blue area, which means the unpopulated area in the middle of the thing, that's Central Park. But right south of that, it's also light blue, and I can tell you that's the place where the most skyscrapers are. The reason it's light blue is because it's a business district. It's a business district that was anchored on the old train networks that brought people into the city and still do, of Grand Central Station and Penn Station. And so there aren't people there because there are huge work buildings there. And that's, of course, because unlike the Alonzo Muth Mills model, where our work skyscraper takes zero space, these skyscrapers do in fact take positive space. But you can see that in general, the densities are a little bit higher, closer to those core areas. You can see the core dense areas along the Upper East Side and along the Upper West Side, and a little bit further off, it gets a little bit less dense, but not at the tip of the mountain, tip of the island, where in fact you still see density. Again, reminding us that the world is slightly more complicated. This is average commutes. This time it looks exactly right. The commute times are high at the tip of the island and low downtown. So this one really looks the way that the Alonzo Muth Mills model is going to assume, that it's cheaper to commute when you're close to the city center than you are farther away. Again, that big green thing in the center is Central Park itself, so it's not a lot of people with low commute times in that. And then this is housing values. And again, the values are higher, closer to work, unquestionably, that looks right. But they're also value with those Tony Central Park Avenue apartments and Central Park and Fifth Avenue apartments that have views of Central Park. And so you see that also in the map as well. And then the prices get much lower further away from the city center. So Manhattan looks better for the things that we're going to look at, where the prices are going to be higher at the center. And we're going to have our model try to fit those facts. This is contract rents. Again, high rents downtown, closer to the jobs, low rents further up where you have longer commutes. One other thing I just want to highlight is you think of it as a relatively small island, but the commutes at the tip of the island are actually pretty long by American standards, right? So these are averaging about 45 minutes up at the tip of the island. They're taking a very long subway ride all down the length of the island. Okay. Last thing I want to just show, this is New York and COVID. So you can see fraction taking public transit, and you can see the number of cases. So in Manhattan, these two things are quite correlated in the sense that the northern bit of the island that you've just seen is the one where the cases are higher and where public transportation is much higher. These are also the poor areas. But in Brooklyn, right, which you should be able to figure out, it's sort of a little bit further down. I don't have a good pointing technology, but this area is Brooklyn. I don't know if you can see that. This area is Brooklyn. In Brooklyn, the areas that have high public transport are not the areas that are high in COVID. And that creates something of a question as to why is it correlated in Manhattan and not in others. One explanation is what's happening in these areas of Brooklyn that are actually pretty rich nowadays is they're really reducing their contact with other people. They're reducing their trips. And in this case, we're looking at the change in trips as measured by the SafeGraph cell phone data. So the high public transit, so two parts of New York are really reducing their contact, at least measured by cell phones, one of which is downtown Manhattan, that rich area, and the second is these near areas in Brooklyn, where they're also relatively high cost, relatively high income. We don't know, by the way, if this is because they're sheltering in place within their homes or they're leaving the city altogether to some country home elsewhere. These are fairly rich parts of New York. All right, the Alonzo Muth Mills model. It is really the starting point for the spatial equilibrium, which is the organizing principle for urban economics. There are older examples of things in urban that you should know about. So, key moments in pre-Alonzo Muth Mills urban. Adam Smith, right, in his ruminations on how in the Highlands of Scotland, every farmer must be his own butcher, baker, and brewer. So that's the idea that, you can't have a division of labor. You can't outsource particular tasks to people who are better at it than you. Sometimes it's phrased that the division of labor is limited by the extent of the market. Von Thunen wrote his The Isolated State in German in 1825. And that's really close to being an explicit within city model, where it has rings of different types of agriculture radiating out from a single center. I know that motivated Paul Krugman a great deal when he started working on this. Alfred Marshall, in his discussion of the causes of concentration of industry, how in dense clusters, as he said in the famous quotation, the mysteries of the trade are as it were in the air. The mysteries of trade are no mystery, but are as it were in the air. Then, of course, you have the central place theory, the early regional scientists, Loesch, Christaller, and others. But we're going to start with AMM. According to John Kane, who was as the senior urban economist at Harvard when I came 30 years ago, there was a lot of competition in the 50s to produce a coherent model of location within a city before Alonso. But Alonso figured out the key trick. I should say, actually, both Sherwin Rosen of the Rosen-Roback model and Bill Alonso are people that I knew reasonably well. Sherwin was actually one of my thesis advisors, and I'll say more about that later. And Bill, I used to have lunch with usually twice a year at Harvard when I first came. So he was an absolutely wonderful man, and he's a loss. His death, which happened a long time ago, is a loss to the field. Okay. Consumers are homogeneous. I will say a little bit about having multiple types later. In the Rosen-Roback model, we're going to deal with idiosyncratic taste for particular metropolitan areas. You can do the same thing for neighborhoods within cities, but the AMM, spatial structure is done with very limited heterogeneity, and if anything, is sort of going to be more general, just rich people versus poor people. Consumers are going to value consumption. Right, that's going to be a traded good with a price that's normalized to 1, and where but you basically want to think of that as that's the amount of cash that they have left over. They're going to value travel time. They're going to want less of that, and they're going to value living space or land. So they're going to have a utility from how much housing they're going to consume. We're going to assume that everyone works in the city center, right, in an infinitely tall skyscraper that uses no land. This is the so-called monocentric city. This assumption is obviously false, right? There are many cities with multiple work centers. I mean, almost every city that's worth anything has multiple work centers, and today people work from home. But this is the model you have to learn first before you generalize it. So hold away your skepticism and learn this model first. Some variable definitions. We're going to use the notation of D, which is going to be where a piece of land is relative to the city center. So it's the distance to the city center. There's going to be a travel time, which we're going to know T or T of D, where T prime of D is positive. The further you live away from the city center, the longer it's going to take you to get to the city. I'm going to refer to linear travel costs sometimes, in which case T of D equals tau times D. So there's just going to be a single parameter, which is going to capture the slope of how travel times increase with distance. I'm going to use H to capture your living space. And we're going to have a price of living space, P sub H, which is going to be a function of D. That price is going to be an endogenous function of distance from the city. And part of the goal of this exercise is to derive the shape of that function. Okay, so this is going to be our first set at the try at the budget set. So this is before Alonso. This is one of the things that the modelers of the 1950s were trying to do. So here you have earnings, which equals time spent working, S, times the wage, or W. And the simple budget set is W times S minus P sub H of D times H equals consumption. And I know I misspelled that. There will be typos, and there may well be algebraic errors in what follows, for which I apologize in advance. And you can excoriate me in the Q&A thing if you actually want to. Money is spent on either consumption of housing or consumption or housing. Technically, this would be an inequality, but of course, Walras law is going to apply because we're going to assume local non-satiation. I can then write down welfare as U of consumption, which is WS minus P sub H of D times H. So this is the money left over after housing, comma T of D. That's the time ingredient, and the utility with that respect to that is going to be negative, right? The derivative is going to be negative. And then H, and that's going to be positive. You're going to like more consumption, more housing, and you're going to like less travel times. We can optimize this over both living space and location within a city. So I'm going to return to the optimal choice of living space shortly, but for now, let's just focus on the optimal choice of location. So you're going to want to have the derivatives with respect to both of those objects are going to be 0, and really throughout this, I'm going to be assuming that second order conditions are going to apply. So we're going to take that derivative, right? We're going to assume that second order conditions hold. Everything is always beautifully, continuously differentiable, and I lose zero sleep over that. The first order condition with respect to distance is going to yield minus P prime of D times H times the derivative of utility with respect to consumption plus the derivative of utility with respect to travel time times T prime of D is equal to 0. Or in more compact notation, the slope with respect to distance has to equal the travel time with respect to distance divided by the amount of housing that you're consuming, multiplied by the ratio of the marginal utility with respect to travel time to the marginal utility with respect to consumption. I think there should be a, yeah, no, that's right. And remember, this is going to be negative. Why? What term here is negative? du dt is negative. The other ones are all positive. Travel time is going up. H is 0. Du dt is negative. Du dc is positive. So any point in which these homogeneous workers live, right? Any spot where they live, this must hold, okay? Now, it might be that no one's living there, in which case this doesn't need to hold, but if I have some kind of positive mass of workers in some location within the city, right? It's got to be that they are indifferent between living there and moving a little bit closer, or indifferent between living there and moving a little bit further away. And so this first order condition must apply, and that gives us a prediction of how prices will change with distance. First of all, they'll go down, right? And secondly, we know they're going to be a function of T prime of D. So if T prime of D is really high, then they're going to go down a lot. So this tells you that, you know, you're going to have a steeper curve when you have worse congestion or when it's harder to get around. It's going to be divided by house size because this P sub H is multiplied by the amount of housing that you consume. So in some sense, the thing that needs to make you indifferent between living in place A and place B is going to be about, you know, going to be the price multiplied by the amount of that housing that you cost. And we'll come back to that later. So this is, you know, and it's going to be multiplied by this ratio of derivatives. So this is fine, all well, as good as it goes. But, you know, there's no actual quantitative thing that you can take out. You can't actually, you know, we don't actually know what du dt is at this point in time. We're going to need something that's a little bit terser than this to start making predictions. And remember, right, the goal with a model is not necessarily extreme generalizability, right? As Karl Popper taught us, like the goal of models is to generate, you know, refutable hypotheses. If you tell me you have a model that cannot be rejected with a model, I tell you you have failed as a theorist. You need actually a model that can be rejected. Otherwise, it can't be tested. It cannot be evaluated. Okay, this brings us to Alonso's leap of genius. Put the cost of commuting into the budget constraint through a time budget constraint. This is exactly the same step that Gary Becker took when he modeled the cost of kids. And it is absolutely brilliant to like start thinking about a time budget set. Okay. The time budget set is really straightforward. We're going to assume you have some stock of time which you can either spend working or commuting. Now, I know in reality, like there's some leisure going on here, but you know, this is simpler than actually allowing you to have yet another choice variable, which is the choice of commuting. And just remember, as you know, modelers in training, right? In general, when you write down your models, it's really important to minimize the number of things that you're maximizing over. Right, so the number of choice variables needs to be small, otherwise you rapidly lose the ability to solve it with any form of pen and paper, right? So if you've decided you're going completely the direction of simulation, that's fine, you can blow it up perhaps, but if you actually wanted to solve a model that you can actually get intuition from, you need 2 or 3 things that you're maximizing over. Whereas exogenous parameters, you can actually blow those up since you don't actually have first order conditions that you need to solve on this. Is it literally true? Certainly not, but it really does work. It does make things easier, and you're going to see that in a second. So earnings are now W times 1 minus T of D. The amount of time you spent commuting, it has to be reduced, taken away from your overall budget set, and that is multiplied by the wage. And when you multiply those things together, that's the amount of money that you have in earnings. You still have to subtract P sub H of D times H, and then you have left H. Now, notice I've gotten rid of any independent argument for the time spent in commuting. That thing is gone. So now the only reason you don't like commuting is you weren't able to spend it working and earning money. Okay, it's something which is actually often done with the sort of Beckerian cost of kids, that the cost of kids is the time that you spend that's not working. Those are the second order conditions. You need the marginal utility of suspected consumption to be diminishing with the amount of consumption, marginal utility of suspected housing to be diminishing with the amount of housing. And you need this second thing, which we're going to joyfully assume those things. Now, the first order condition with respect to distance is now going to yield this thing. So it's minus P prime of H times dUdC minus T prime of dW times dUdC. So instead of having a dUdC and a dUdt, right, which we had before, remember you had the fight of utility against consumption. You have the utility effect of consumption weighing off against the utility effect of time. These are both denominated in dollars, they're both denominated in consumption, and they just drop out. And that's the beauty of this. Anything regarding the utility terms disappear on their own. And those things drop out, and so you're left with this incredibly simple, incredibly beautiful thing. That all you have is the price of housing, how it changes with distance, times the amount of housing you consume, is equal to minus 1 times the amount that travel costs increase times the wage. The increase in the cost of housing exactly offsets, well, it should be the decrease in the cost of housing exactly offsets the added cost of commuting, or if you're coming closer, the increase in the cost of housing exactly offsets the reduced cost of commuting. No utility terms are even included, and it's all perfectly estimable. So this is really a triumph for Bill Alonso. You have compensating differentials and equations that can be exactly brought to the data. And I can't think of anything that one can ask for in life beyond that. Okay, so let's just do a simple example of this. Let's turn off the endogenous choice of housing. So now we're fixing by straight out executive fiat. And remember, when you write down your models, it's your model, right? You are the dictator of your model, and you actually get to make, whatever assumptions you want to. So now, no, you don't get to choose H anymore. It's just fixed. Everyone consumes exactly 1 unit of housing, okay? And these are the two things that we go back and forth on in urban. There are sort of 1 person, 1 house models, and there is a sort of endogenous H model, and both things coexist within the literatures. If housing is equivalent to land, that's going to kill any ability to predict things about density. But if builders deliver units by building up, then you still will have predictions about density. So we will still all live in the same units, but in places where land is valuable, they're going to stack the units on top of each other. And in places where land is cheap, they're going to make them flatter. And we'll get back to that in a second. So 1 person, 1 household, right? 1 household, 1 house means there's no intensive margin. The H terms drops out, and all you have is that P prime of D equals minus T prime of D times W. The change in price offsets exactly the wage-weighted increase in the time cost. So that's the heart of the Alonzo-Muth-Mills model. And this is just what it is in this case. So you've got distance to the employment center. Along the x-axis, you're showing the distance. And the red line shows your willingness to pay for housing based on distance to employment. So it's going down. Okay, and in this case, I've assumed the linear commuting cost, it's going down because you've got to add back in your cost of actually getting to the city center. You're willing to pay less because locating further away brings in this added cost. We can be even simpler, reading the price curve flat out of the indifference curve in this flat H thing. So if their spatial equilibrium assumes if I have homogeneous consumers, everyone gets the same utility. That's the heart of it, right? There's no free lunches in where you locate. So if I've got some kind of measure of consumers who are locating in different points in the city, they all need to get exactly the same utility level. That is the spatial equilibrium assumption, and that's why Alonzo gets some credit for this. We typically call this U bar, which is reservation utility. I will come back to this in a second, but in the so-called open city models, U bar is an exogenous parameter, right? Because people can flood into the city. And so that this flooding into the city ensures that people get the same utility by living in the city that they get outside. In the so-called closed city models, then U bar is a endogenous outcome. It's determined as a function of the number of people living in the city. Okay, so if U of 1 minus T of dW minus PH of D, comma 1 is equal to U bar everywhere in the city, gosh, that means that 1 minus T of dW minus PH of D is constant over space. So that means that if I've got 2 locations, you should see exactly the same total value of 1 minus T of dW minus PH of D. So to implement that, let's take the central location. Let's take the center right next to the skyscraper and assume that at that location, at the house that's right next to the skyscraper, there are no commuting costs. You just walk out your day, you walk out in the morning, you're right there, bang up against your job. So in that case, what's 1 minus T of dW minus PH of D? Well, it's just what you're seeing over here. It's W minus PH of 0. And that's got to be equal to 1 minus T of dW minus PH of D every other space in the city. So these two things need to be equal. So from this, we know that PH of 0 minus T of times W has got to equal pH of D. At every point, the sum of commuting costs plus housing costs has to equal pH of 0. And that's exactly what you're seeing here, right? So if the transport costs are linear, then you sort of start here and just draw a line across, and that's the total cost. And the missing triangle here are the transportation costs, which are going up linearly with distance to the city. Okay, now, now we're going to make a second point, which is a little more sort of arcane, but I think important for you to understand. Hicksian, you presumably, for those of you who are graduate students in economics, in your first year, someone made you suffer through Hicksian demand curves, which of course are demand curves which are defined not with a fixed level of income, but a fixed level of utility. So changing prices and holding utility constant, looking at what happens to demand. They may have seemed like very arcane things. Who in the world ever sees a situation in which you have Hicksians where you're holding utility constant? Well, guess what? This is your moment, John Hicks. This is the moment where actually Hicksians show up because, in fact, the demand curves that you get out of spatial equilibrium models are typically Hicksians because at different spots along the city, in different spots in space, utility is being held constant. So let's return to flexible housing space. So here you're getting to choose H. And now we're going to look at the first order condition with respect to H. So this is going to set the marginal utility of consumption times the price. So that's the cost of buying more housing is going to be equal to the marginal utility of gaining more housing. Or in the notation that I have down here, minus pH of D times DUDC plus DUDH has got to equal 0. Okay, so I'm starting with this first order condition. Everyone with me? I'm starting with the first order condition. Okay, now I'm going to do the trick that we always do when we try to sort of, figure out comparative statics and economics, which is we're first going to take this first order condition and we're going to use the implicit function theorem to define an optimal level of housing, which is going to be H star of D. So wherever you are, you're consuming the optimal amount of housing. And using subscript notation for the literature for these derivatives, I can write this as minus pH of D times U sub C. That U sub C is the derivative of utility with respect to consumption, plus U sub H. That's the derivative of utility with respect to housing. So that's du dc and du dh. That's still got to equal 0. That's the first order condition. And now we're going to differentiate that derivative totally with respect to D. So we're going to ask, how does housing consumption change as you move further away from the city? So I'm running this thing through totally. This is what I get. The U sub CCs are the second derivatives and so on, all using standard subscript notation, and I'm dropping arguments ruthlessly in terms of noting it up. And this looks kind of like a normal comparative static for a demand curve. The denominator, of course, is positive. That was ensured by the second order conditions. The numerator has two terms. The first term is basically a standard price effect, right? It's the fact that as I change D, I'm going to multiply U sub C times minus P prime of H. And if I didn't have the second term, I would know that as I get further away, right, since the price is going down, this term is positive. Price is going down, multiplied by -1, this term is positive. And this is saying, well, things are cheaper, so you should buy more. But usually, when things get cheaper in a comparative static for price, then there's an offsetting income effect. And that's captured by the next terms. The fact that the price of some good went down, right, means that you're going to, you're functionally richer, and that will change your consumption. That's how we get things like luxury goods or Giffen goods, where you can get things going the wrong way, even if the income effects are large enough. But take a look at the thing that's multiplying your normal income good things, okay? That minus WT prime of D minus P prime of H. Remember, the spatial equilibrium assumption required that P prime of H of D times H equals minus T prime of DW. Those two terms exactly equal one another. And so the second part of this thing, this disappears because you're not becoming richer or poorer along the path of distance from the city. Everyone on that path is getting exactly the same utility. And so we are changing prices, but holding utility constant. And that is a Hicksian. And that's why you can fundamentally sign this, how housing consumption changes with distance from the city. It's always going to go up, right? You're always going to consume more housing because the only difference as you get further away is I've lowered the price of housing to you. And that, in that case, the straight price effect dominates. And that's why people consume more housing. That's why density is going down as you move away from the city, because you're shrinking the price, and that's causing people to consume more housing. All right, so spatial equilibrium models often give you Hicksians because Hicksian demand curves hold utility rather than income constant. In a spatial equilibrium model, you're also holding utility constant. So as price changes, there's no offsetting loss in utility, and you get pure prices. Since you consume more housing as you move away from the city center, the relationship between housing and price and distance from the city center is decreasing and concave. And that's because, go back and look at here, okay, this H thing is getting bigger as you go away, and that's causing this thing to flatten out, right? So if you divide P prime of D as minus T prime of D W over H, and as H gets bigger, that thing is getting smaller and it's flattening out. Okay. Housing supply. So far we've considered the demand for usable space, not the demand for land. To move this into a purely spatial structure, we actually need to bring in land. Okay, so one variant, which is often how it's taught, and I will get to a version of this at the end of this segment, is to assume that H equals L. People are just buying land and living on the land. So possibly, you know, people are just living in cheap tents that were given to them, and they just, you know, spread their tents out in different space of the land. And so some people are buying further away. They're having more land to pitch around their tent. And when they're really close to the city center, they're all in tents that are right next to each other. As theory, it's a little funny, but it's perfectly fine. And in many cases, it's the most natural way to teach and learn this. The alternative is to write down a supply curve for usable space. And I'm going to do that now. So for example, assume H is supplied using land and capital. The land is bought at an endogenous price, PL of D, and that price of land is going to be a function of distance. Height is then added. And so the amount of space that a builder gets, let's say they bought some plot of land L, is going to be little h times L, where little h denotes the height of the building. So like you got 1 acre of land or 1 hectare or 1,000 square feet of land, and you build to 10 stories, this assumes that you can then get 10,000 square feet of buildable space to build. And we're going to assume that the cost of building up is going to be a power function of height. I'll talk a little bit about that technology in the next section, but we're just going to assume this for right now. And that power function has got to be greater than 1. So you get to an interior solution in the optimal height. If that delta is less than 1, then you're either going to, you know, not build at all or build an infinite amount. And so you also often would just have h to the delta times some fixed cost, or a constant plus h to the delta times land. I'm choosing the simplest thing possible so that you're going to get a coherent solution without extra parameters. And so developers are going to maximize to buying land and then choosing height. PH of D, HL, that's revenues. They're going to sell the housing and they're going to get H times L of housing. They're going to have to spend H to the delta times L on their construction costs. And they're going to have to spend PL of D times L on their land. So they're buying land for PL of D. They're paying for the construction costs, H to the delta L, and those are the costs, and those are offsetting their revenues. That's going to yield a first order condition of P with respect to H, and notice the L's dropped out when you did the first order condition of PH of D equals delta H to the delta minus 1, or H equals PH of D over delta to the power 1 over delta minus 1. And notice here, you've got to have that delta greater than 1 or else it doesn't make sense. So this gives you that if the price of housing is falling with distance from the city, then heights are going to be falling with distance from the city, right? So the H is monotonic in the price. So this is giving you that you're having this density relationship with proximity, that density is going up. The buildings are going to build up. And this is true even if every person consumes the same amount of housing, this will still be true, because as long as you have prices that are higher closer to the city center, you're going to have higher buildings to deliver more space to consumers. And that's exactly what we see. So this is Manhattan. A lot of this stuff, remember I told you a little bit earlier about, you know, these areas where you didn't see people. Well, that's where those big tall buildings are up there. You can see Central Park right above it. Also, there's big buildings down here. And that's a little bit misleading because, in fact, these are work buildings. But you can see still there's plenty of residential high rises here along the Upper East Side, and they're lower further away from the city. This is Boston. Boston's central business district is right here. And you can see the density is falling off slightly as you get further away from the city as well. Building technology matters. So the skyscraper made a huge difference in our ability to build up. This is what 19th century Boston looked like. And as you can see, it was a much flatter city. The introduction of the skyscraper, which really married two forms of construction. The skyscraper has a steel or cast iron frame that enables you to sort of build up and reduce costs by just hanging the rest of the building on top of that frame. And of course, you also needed Otis's safety elevators as well to make skyscrapers work. Okay, so you plug this optimal height into the builder's profit condition. You impose a zero profit condition on the builders, so they're not allowed to earn positive profits in equilibrium. And that's going to give you a price of land that's implied by the builders having to earn zero profits. And you can work through that on your own. And I may well have made an algebraic mistake on this, but the basic structure of how you do it is right, that the price of land is such that the builders have to earn zero money. The elasticity of land's price with respect to housing price is more than 1 for 1, really. So this thing, so d log land price, d log housing price, is multiplied by delta over delta minus 1. So that's the elasticity, and that's going to be greater than 1. And that's because as you get closer to the city center, you're building up more and more. And so you're getting more and more value out of that space because you're adding density. Note that all profits in the city go to the landowners. And that's reasonably general in urban models, at least those without a whole lot of place-based taste heterogeneity. It's sometimes called the Henry George theorem, which is that basically the land gets all the rents. And that's credited to Richard Arnott and Joe Stiglitz in 1979. An aside on heterogeneous preferences. No, I'm not going to do that. There could be heterogeneous preferences on living in the city, but I'm not going to talk about them right now. As a final aside, it's often assumed that there's an agricultural value of land PA that puts a floor on the value of land. This will determine the edge of the city, which we can denote D bar. And that's determined where the price of agricultural land, so that's the value of it for growing stuff, has got to equal the price of the urban use. And so you have this sort of, equilibrium condition that you can use the land to put apartment buildings, you can use the land to grow stuff. And at the edge of the city, those prices need to be the same. And so this is going to determine the edge of the city. The D bar is going to be the point in which those prices are equal. So closing the model, there are two canonical structures that I've already mentioned. Open city. We assume the city is free, people can move in from somewhere else, and we're going to look at a spatial equilibrium across cities, except we don't model those other cities here, okay? All we say is that there's an infinite flock of people who are able to come and deliver U bar, and as long as the utility in the city is higher than U bar. And the city population is going to equilibrate because if this city has a utility that's higher than U bar, then more people are going to rush in. If it has a utility that's lower than U bar, more people are going to rush out. Okay, and then the city population is going to be an endogenous outcome. That's the open city model, the open city AMM version, has people rushing in and rushing out. The alternative in the closed city model is that you fix N. So you have a fixed number of people in the city, they can't go, they can't come, and then utility in the city is going to be an endogenous outcome. Oh, here's where this slide is supposed to come. This shows how you can use a distribution of preferences to go between these two extremes. So there's a parameter in this thing that shows that, when the parameter goes to infinity, you get the open city, and when the parameter goes to 0, you get the closed city. Okay, the open city model in operation. Here are the easy things with the open city model. We know that this utility has got to equal U bar. So this is going to pin down pH of 0 because U of W minus pH of 0 times H star of 0 comma H of star of 0 has got to equal U bar, and the first order condition for H has got to hold. Okay, so we know the absolute center of the city has got to exist. And so you've got a system of two equations and two unknowns. If you wanted to give me specific functional forms here, we could explicitly solve this thing out, right? So we've got pH of 0. You can also even take comparative statics on this, differentiating both of these equations, and show how pH of 0 and H star of 0 change with W and U bar, which are your only two parameters in this right now. And with that, everything else is technically defined. So we've characterized an equilibrium, but it's a little difficult to work with. So I'm going to work with two simple functional forms. First is going to be the fixed housing consumption at the individual level. And the second is going to be a particularly nice functional form, which is utility is going to be consumption of regular goods plus alpha times ln of H. And I'll come back to that later. In the open city model with fixed housing, we have U of 1 minus T of dW minus pH of D comma 1 equals U bar. That's going to give us U of W minus pH of 0 comma 1 is equal to U bar. And we can then define C hat of U bar as the value of C at which U of C hat comma 1 equals U bar, right? So that's defined exactly by that equation. And then with that C hat of U bar, we know that W minus C hat of U bar has got to equal pH of 0. And for all other distances, 1 minus T of D times W minus C hat of U bar has got to equal pH of D. And so in this one person, one house model, we have now solved for the price of housing within the city just with this sort of simple equation. That's characterizing the prices. Consequently, you know, this at the city's edge, we have this equation that holds, or which is that PA is equal to what the price of land is at the city's edge. And I'm going back earlier to our relationship between the price of housing and the price of land, and I'm plugging in the price of housing with the price of into the price of land equation, and then I can invert that, since it's a simple power function. I can invert that with t inverse of this thing, and that's going to solve for the city's geographic size. So we've now solved for the size of the city. How many people are going to live in the city? Well, we know what the density is. That's going to be determined by the optimal building on the part of the developer. I can then plug in my pH of D in that case. And so if this is a circular city, we just integrate up of the amount of density between the inside of the city and the outside of the city, which we've solved for this price equivalence between agricultural and urban land. And we just integrate the number of people living at every spot, and we've gotten the city. So we've described density, right, which is going to be higher close to the city. We've described total city population, and we've described the geographic spread of the city. Now, you may wonder, what's that 2 pi going on here? I didn't define pi as a parameter. This pi, this is 3.1415927. This is the real pi. And the reason for that is this is a circle, okay? And when you're integrating the space out and you want to figure out how much space there is in the circle, you know, you have 2 pi r in terms of each thing that you're adding on, right? So this is the amount of population that you get. And so we've actually explicitly solved for this. And we still don't have a pretty functional form yet, because we don't actually know what T of J is. So if you were teaching this to undergraduates and you really wanted something like beautiful and simple, you'd assume that T of D equals tau times D. So you just had this linear price. With that linearity, you get 1 minus tau times D times W. So that's the income net of commuting costs. Minus C hat of U bar, that again is the C hat that works the spatial equilibrium outside the city, that makes the open city model hum. And that has to equal pH of D. Okay, and then the edge of the city is just equal to 1 over tau, and that's of course what inverting does when it's just a linear function times this other thing. So you have an explicit functional form for the size of the city, and you know, and you can then go back and integrate up the density, and you actually have a closed form solution for that. If you had no height technology, and so everyone consumed exactly 1 unit of land, then it's just really easy. The total population is just pi d bar squared, and since people are just consuming land, and you have this determines the edge of the city, as before, d bar is equal to this thing, and so total population is just this. And so population is rising in W, declining in the reservation utility, declining in the agricultural value of land, and declining in the transportation costs. And so that's the simplest version to get you a really tight closed form solution. But let's just do that for undergraduates. We're not going to spend more time on this. The sort of fancier way was taking this d bar and then running this integral in order to get things. Okay, and you can show them graphs. So this is a slightly different notation than the one I used. I don't want to focus on this, but this is, you know, just showing the price going down linearly. In this case, you're actually paying for structure C, and then you have the agricultural rent, which is determining the edge of the city. Okay, and in this case, there's got to be a difference between your willingness to pay and the agricultural price, which is determined by the cost of building the structure. And this just shows what happens as the city gets more productive. So that's a rising value of W. This curve shifts out, and you get a bigger city. Okay. Fixed housing consumption, the closed city model. Okay, in the closed city model, you don't know utility, but you do know the population. You continue to have pH of 0 minus T of dW equals pH of D, where housing is 1. Okay, density is going to continue to satisfy the same function. You're going to continue to have D bar, which is going to be the T inverse of this expression. And then you're going to close the model by imposing N equals this integral. Right? This was the same integral you had before, but before you kind of knew what pH of 0 had to be to equalize utility between the city and outside. Here, you find pH of 0 that satisfies N, okay? And that's what's gonna work to solve the model. So that's how the closed city works. And so, you know, just to take a really easy case, if height is everywhere 1, transportation costs are linear, so then in that case, N must equal pi d bar squared, or d bar is just literally equal to the square root of N over pi. You know that at the city's edge, you're going to have a price of PA, and that's going to have to equal pH of 0 minus the commuting costs of getting there, which is tau W times the square root of N over pi, and that's D. Or pH of 0 has got to equal the price on the edge plus the commuting cost to get in. That's, again, the spatial equilibrium within the city that's implied by this. So that's just a very simple version of this. And the basic structure is in the open city, you start with prices at the city center, and that implies the edge of the city and population. In the closed city model, you start with population, and then you solve for the edge of the city, and that implies the price at the city center. Okay, one last thing, and then I'm done on this. Let's assume throughout this case that utility is equal to is quasi-linear in consumption, and you add on a natural logarithm of housing times h, and we'll assume that transportation costs are linear in distance. Overall utility then is just going to be W times 1 minus tau D minus PH of D H plus alpha ln of H, right? So you have this concave natural logarithm that's giving you housing. The first order condition for D is then going to imply PH prime of D times H equals minus WT. That's the same as it's been before. But the thing we're getting now is the first order condition for H is just going to give you that alpha over H, because of course the derivative of the natural logarithm is just 1 over the thing. So 1 over H times alpha equals PH of D. So now I've got P prime of D is equal to minus W tau over H. P of D is equal to H over alpha over H. I take the ratio of those two. Bingo, I've got P prime over P is equal to minus WT tau over alpha, and that's a constant. I know how to solve the differentiable equation, and you should too. And the solution for this is PH of D equals PH of 0, which in this case is just the constant of integration, times e to the minus W tau over alpha D. So the price is going to be decreasing exponentially with distance from the city center. And that means, because the price is equal to alpha over H, that housing consumption is going to be increasing exponentially with the distance from the city center, which motivates using log linear functions for our empirical work. So the log of P is equal to the log of P0, P at price at 0, minus a linear function of distance. And the housing is going to be the same. With flexible city consumption, then you plug this in the open city model, you find out utility at the city center, you set that equal to U bar. And with that, we have a solution for PH of 0, again, by imposing that utility at the center is equal to the reservation utility, just like we did before. The urban edge is going to be found by then taking that PH of 0, looking at what that implies for price at different distances from the city, and then we're going to impose that has to equal PA at the city edge, and that's going to solve for D bar, and that's our solution for D bar. Okay, that's gonna give us how big the city is. And then population is going to solve this thing. So we're just going to integrate of the density. And this is, oh, I should have said, I was going very quickly. In this case, people are just living on land and living on tents. So we're not having any building. The only reason you're getting congestion is because you're getting density going up is because people are living on less land. So in this case, we just integrate the number of people living at each spot, which is just 1 over the amount of land they're consuming, or 1 over the amount of housing they're consuming. And then we just integrate that up. This circular city is slightly more annoying than a linear city in this case. You'll see the difference is I have 2 pi j here, and here I've dropped that term for the linear city. And in the linear city, we can just integrate that, and Bob's your uncle. You have n is equal to this thing. So again, you have a solution for the overall size of the city. It's going to be increasing in the wage. It's going to be decreasing in U bar. It's going to be decreasing the agricultural value of the city. And so we've just solved our equation. If you wanted to go the other way and start with the closed city, you would have, again, take this thing, and then you invert it to get PH of 0, which would be a function of n. So in one case, you're going to solve first for price at the center, and then the edge, and then solve for population in the closed city. You're going to solve first for the edge, and then you're going to find the price at the center that satisfies the population constraint. I'm not going to say very much about this. You can do this with multiple transportation technologies. If you do, so there's some nice transportation technologies, you end up with different zones. So let's say there's a high fixed cost technology and a low fixed cost technology. The high fixed cost is going to lower your marginal cost of commuting. And then in that case, you're going to have people who are living close to the city center, and people who are driving, living further out. And this shows streetcars, and this just shows land per person going up as you go away from Chicago using that log linear function. But it's not true in Houston. And the reason it's not true in Houston is, and this is my final comment on AMM, that AMM is a beautiful, wonderful model, and you've got to know it. But in many cases, it's false. And the reason why it's false is that Houston is not a monocentric city. Okay, people don't come to one skyscraper. There are employment areas all over Houston, and they're going to it. And that suggests the limitations of that. And I'm going to stop there and move on to the Rosen-Roback model later. You can amuse yourself by looking at the pictures. I don't know if we have time for, did you want to give me one question, guys, before we take our 5-minute break?
Sure, Ed. we can take one question. Actually, there's two people asking pretty much the same question, has gotten a lot of interest, which is, how do we square equalization of utility across space with income inequality in cities? Do the people living in high-rise buildings and the poorer areas really have the same utility, even after considering rent price differences?
So if there are multiple income groups, okay, there is no claim that the rich people in the city have to be earning the same utility as the poor people in the city. In fact, we have, I suggest either the Leroy and Saint-Sully paper or my paper with Kahn and Rappaport on, there's also a nice paper by Bruckner, Thies, and Zanu on why rich people tend to live further out in the US and poor people tend to live closer to the city center. So there's a whole literature about income and where you live in the city. But no one ever assumes that the rich people and the poor people are getting the same utility. That would be madness. And the rich people who live in fancy skyscrapers are going to be having a different utility from poor people who live in tenement houses, of course. The assumption is, though, that if you see rich people living at two locations within a city, the rich people in those two locations are getting the same level of utility. Otherwise, they'd move. Similarly, if you see the poor people living in one location versus the other, the poor people would move. And so it's not our claim that different people get the same utilities, but that the same people within classes. Now, why did I do this model with one income group, one set of homogeneous consumers rather than multiple ones? Well, for obvious reasons, which is this was complicated enough as your first exposure to AMM, and multiple income groups make things harder. But I do think that this type of model, and again, take a look with my paper on why do the poor live in cities with Kahn and Rappaport in the Journal of Urban Economics, I do think this question of why it is that the poor live in particular areas of cities is absolutely central, partially because neighborhoods shape the experience of people within cities, and partially because the clustering of African Americans in particular segregated areas has been strongly associated in my work with David Cutler from 20 years ago, or the work recently of Raj Chetty, using the Opportunity Atlas, with lower levels of upward mobility. So all of those questions are sort of central to urban, but you can't walk before you run, you can't run before you walk, and you need to do the simple model with one class before you get to multiple models. And that's the answer to that question.
And we have one question that has received a lot of upvotes, so maybe we can take that quickly.
Okay, done.
Today, which is about Chinese cities, and in particular the observation that after subway stations are built in a community, the nearby housing prices often rise much more than the reduced travel time would suggest. And do you have a view on that, on what causes that? Is that due to housing price bubbles, or are there other channels that we should think about?
So first of all, I mean, again, to refer you to sort of Chinese housing prices, I urge you to look at my my paper with Andre Schleifer and Yoran Ma in the Journal of Economic Perspectives called a Real Estate Boom with Chinese Characteristics. What you have to ask about prices are likely to be a forward-looking object, right? Prices are always a forward-looking object. And there's nothing sort of dynamic about the model that I've written so far. But when you look at someone buying, they're asking not just about what's going on today, but they're asking about what's going to happen with this land in 20 years from now. And if you think that the Chinese who are buying today these apartments that are near the subway stops, maybe right now their time isn't worth enough to justify the prices. But if China has 5% growth every year, it means that their incomes are going to be doubled in 14 years and quadrupled in 28 years using the rule of 72. So with those higher incomes, maybe these prices can be justified. And if you're discounting those future flows at a low enough rate, then you can certainly get a very large predicted price impact out of a modest impact in travel time if you think that wages are going up over time in a continuous way. So do you want to ask me another question during break? Is that unfair, or? I'm
happy to do that. So the next question would have been, how is the city center defined in those models, or chosen? Is it entirely exogenous, and is there something interesting to say about it?
Yeah. So this takes the existence of the city center as being completely fixed and exogenous. Empirically, it's an interesting question about how you define it. There's a census of governments item from 1982, which is often taken as being the spot. Sometimes it's relatively obvious where you define the city center, but in some cities it's a little bit harder. I guess in London you would take the square mile and maybe Threadneedle Street as being the city center. In New York, there really are two central business districts: the older one, which is anchored by the port downtown, and the newer one, which is anchored, as I said earlier, by these rail stations. But the AMM model is not a model of endogenous location of the central business district. There are such models within urban, but it isn't one of them.
Great. So maybe one or two more, and then we should start with the second half of the lecture, I think. These are really quick questions. So the second one was, how plausible is it to assume builders make zero profits? Do we have evidence, empirical evidence on that? Yeah.
Well, it's a good question. The assumption, the zero profit condition, which is applied ruthlessly in all of microeconomic theory, is both ubiquitous and likely to be false. I mean, the normal way we square this in our standard models is we assume that we are omitting a factor of production, which we sometimes call entrepreneurial capital. And what you think are profits, I think are returns to entrepreneurship. And so you just add that extra ingredient into the production function so that the extra profits are returns to that. And that's how you can square the idea of sort of zero profit equilibrium. In the case of building in a featureless plane that's not regulated, it's a pretty darn competitive industry. And so it's probably not unreasonable to believe that those profits get put away, get competed away. The massive numbers of builders in most parts of the US. Now, what's different in terms of real estate in cities is it's a highly regulated industry. And there are people whose primary comparative advantage is their ability to work the regulatory system. And that regulatory system provides them with the ability to, earn some form of profits. So that would not be the case in a richer model of that. Again, the thing is, I want to stress this about model building more generally. We can enrich things in lots of different ways. We could add in housing regulations. We could add in heterogeneity of builder productivity, and so you have some builders who are earning, who are inframarginal and earning rents. All of that we can do. But when you think about it, when you ask about it in terms of models, you need to sort of face the challenge of like, you're going to need to write down that model, and you're going to need to work with that model, and you're going to need to interpret that model. And the more stuff you want to add in, the more quote unquote realistic you're going to make it, the harder it's going to be for you to do that. And so we've delivered a model with AMM that delivers the things that we set out to deliver, which is the relationship between density and proximity to the city center, and prices and proximity to the city center. And we deliver that model, and we've delivered testable implications. But unquestionably, it's a jump between reality and that. Okay, so shall I move on to Rosen Roback?
Let me ask you there's a very timely question, I think. Maybe you could just provide some references, and then we move quickly to the second part of the talk. So the question here was, what kind of extensions or papers are there, or what does this model have to say about American cities shaped by a history of redlining and segregation? Could you point us towards
there's plenty of things on redlining that have come out recently. There's a book called The Color of Law. That would be a place to start if you didn't know it. You might also be interested in The Rise and Decline of the American Ghetto, which is my paper with David Cutler and Jacob Vigdor in the Journal of Political Economy in 1999, that looks at the path of segregation in the US over the past 120 years. We typically think of those models that are more about shaping who lives in which buildings, not about the shape of the buildings themselves, but there's no question it could do the latter as well. And the AMM model is really about the shape of the buildings more than it is who exactly lives in those buildings. But it's certainly the issue of race in the American city is very, very rich and very, very important and very, very worth studying. But you need to learn the basic models first, which is why they asked me to teach these things and not to do my work on segregation in the US.
Perfect. On that note, I think we should just go into the second part of the lecture.
On that note, we have Leah Platt-Boustan speaking next week.
You do.
I'm sure she'll address these issues.
Eminently qualified, and former one of our PhD students from Harvard, now a very distinguished urban economist and an economic historian at Princeton. Yes. Okay. So, but Leah also needed to learn these models first. Okay, which is why we're sticking with these models in order. Okay. So the full Rosen-Roback model. Remember, the Rosen-Roback model is an equilibrium across metropolitan areas. So we're no longer paying any attention to where you live within the city. In fact, the city is completely homogeneous. Okay, it's got one price of housing within the city. It's got one price of non-traded goods. There's going to be a spatial equilibrium for workers and consumers who are themselves mobile across cities. So you can't have a city delivering extra utility in some area because otherwise people would flock into the city. There's going to be a zero profit condition for firms or a spatial equilibrium for entrepreneurs. We're going to impose a zero profit condition for firms. How realistic is this? Probably not. but it's by far more reasonable than most of the easy alternatives. And we're also going to keep on with this zero profit condition for the builders who are supplying housing, or alternatively who build the traded goods. There are lots of other alternative ingredients that you can throw in. One of the sort of nicest ones is that to then make local policies, let's say the policies that determine how difficult it is to build, be endogenous and determined by who moves into particular areas. You can have endogenous agglomeration economies, endogenous amenities, all these, as Rebecca Diamond does, all of these things are possible, but we're going to start with a very bare bones version of it. This is the spatial equilibrium in its old style. Everybody is identical, okay? There's only one type of person. They're choosing between different cities. When they locate in an area, they're getting an indirect utility function that's going to be a function of income, prices, and amenities. Income is Y, prices are P, and theta is indexing amenities. Theta is standing in for the time spent commuting in this area. And it's going to be exogenous. And this is in, for example, Jennifer Roback's 1982 Journal of Political Economy paper, but it's earlier sketched out. Jennifer Roback was, like me, a student of Sherwin Rosen's, and Sherwin sketched it out earlier in a 1979 paper, which draws from his work on hedonic pricing in the JP in 1974. Utility must be equalized across space. And so again, we have our old friend, the reservation utility must equal utility everywhere. So V of Y sub C, P sub C, theta sub C has got to equal U bar. So that's our spatial equilibrium condition. Now, is it literally true that people are happy everywhere? This is actually self-reported happiness across the United States. And there are areas where people say that they're happier than other areas. So the Deep South, for example, says that they're happier than the Rust Belt. So you can either think of this as saying that, there are differences in utility, or you can say that, what's happiness is not the same thing as utility, which is certainly something that I believe, that, whatever it is I maximize, it isn't happiness. And I think there are things in life that are more important than being happy, like figuring out how you can be of service to the world by learning things about the world and teaching them to the world. But that, of course, doesn't mean that I literally believe the spatial equilibrium assumption holds everywhere, no more than the no arbitrage assumption holds everywhere in finance. It is an approximation, and it's probably not a terrible one. Okay, if this is the case, then V of Y sub C, P sub C, theta sub C has got to equal U bar. And we can take some simple derivatives to build some intuition. So let's take a derivative with respect to theta C. So we're asking, this can be interpreted as what happens as the amenities in an area go up, what happens to the difference between its income and its prices, okay? And in this case, we're just grouping the price and Y together. So this is everyone's buying one house and they're paying P sub C. So if you take this derivative, you get D of this net income D theta equals minus V sub theta over V sub Y. Okay, so it's the ratio of the marginal utility of amenities divided by the marginal utility of income. Okay, so higher amenities are associated with lower real incomes. And this is sort of a first order thing that you should keep in mind about how spatial equilibrium works. If something is nice about a place, then something else has to be bad about a place. That's the fundamental logic of it. So if an area has nice amenities, then it's got to have lower real incomes. Is that true? Well, this is income and climate across the US. Those places that are warmer generally pay lower incomes. I don't know, is it the right slope to offset utility? I don't know. But certainly it has been historically true that this is income, but it's also true that real incomes corrected for local prices also go down with it. So it doesn't seem to be a terrible implication. Holding amenities constant, higher incomes are going to be equal to higher prices. So you're going to have an exact price offset by an equivalent increase in income. So any income is offset by an equivalent increase in price, holding amenities constant. And so that's why you expect to see things like this. So this is the relationship between housing prices and income across areas. So there are some areas like San Francisco, which seem to have prices that are too high relative to income, but by and large, it doesn't look terrible. There is a question about whether or not this is the right slope. I personally think actually the slopes feel a little bit wrong in terms of the price of actually expensive housing in high income areas feel like they're a little bit too high, feel like a little bit too low relative to the extent of the incomes. But then again, I'm not controlling either income or housing price for anything that's interesting about it. How different are the people, how different are the housing, and so forth. Okay, now the new style is to drop the assumption that everyone's identical, but only partially drop it, okay? So you're gonna partially drop it in the sense that everyone is kind of identical, except some people have an idiosyncratic taste for particular locations. So you have an idiosyncratic or random place-specific preference that follows a type 1 extreme value distribution with a density e to the minus this thing. Okay, so individuals are identical except for their heterogeneous tastes for particular locations. Then the share of the population living in city C prime is this thing. And this is the standard logit formulation that you get out of the type 1 extreme values. And again, look at her 2016 AER paper. And this is actually fine too. What gets more difficult is if I have heterogeneity of multiple types. So I've got high education people, low education people. I have people of different groups. That is doable, but it tends to be hard for a variety of different reasons. And the sort of pretty math that works with the Rosen-Roback model tends to fall apart pretty quickly when you have a discrete number of types. Whereas this won't be particularly hard for us to work with at all. This is going to give us an upward sloping curve in terms of the supply of individuals to be in an occasion. Okay, that's spatial equilibrium. So the first version is utilities are literally constant for everyone. The second is utility is constant subject to a place-specific idiosyncratic preference. Okay, now, free entry condition for firms. Guess what? Utility is going to be Cobb-Douglas, constant returns to scale. Why? Because it's easy to work with, because it's going to get rid of all the excess profits. AC is our city-specific local productivity. Maybe it reflects some agglomeration economies in the background, but we're not going to deal with that right now. K is going to be traded capital, which is available everywhere at a price of R. L is going to be labor, okay, which is going to be hired at a city-specific price of Y sub C. Remember that Y that entered into the consumer's equation? That's coming from here. It's not an exogenous thing, it's an endogenous thing, and it's going to be determined by the labor market of workers being hired by firms. On top of this, I'm going to throw in something called non-traded capital, which is going to be available with a fixed supply of Z upper bar sub C in that area. So this is going to be a constant returns to scale technology, but you're still going to have profits that are going to come from production, but those profits are going to be going to the owners of non-traded capital, which again is a variant of the Henry George theorem at play. Free entry for firms, the price of the traded good is normalized to 1, and that's going to give us a local labor demand of the following form. We're going to have some constant plus weighted average of the A sub C, weighted average of the Z bar sub C, and we're going to be subtracting off the amount of workers that you hire. And that's just a labor demand curve. As you hired more workers, the marginal product of labor goes up. Does it matter how many firms there are? No, okay, because it's a constant returns to scale technology. You can slice this up and say that there are 10 firms or 100 firms. The one thing I cannot let you have is local monopoly. These firms must be price takers with respect to all of these prices. Otherwise, this model doesn't work. But as long as you have 2 firms and they're Bertrand competing with each other, then you're just fine, okay? All the profits will go away to the owners of the Z bar, and you're going to have this equation hold. Now, you see this funny Greek symbol that looks like a trident here. You will see a lot of these funny symbols going on. That's because these models tend to generate a lot of nuisance terms that I'm not fundamentally going to care about. I'm going to care about these things which are city-specific parameters. These big Greek things are going to be all these things that are not city specific. And so they're going to vanish in the equations that we're going to ultimately get to. So that's our local labor demand curve. That's one of the 3 curves that's going to be shaping our spatial equilibrium in this case. If you wanted to allow for agglomeration economies or some other form of externalities, you could then vary your AC to create some more primitive AO comma C. And then you'd multiply that by the overall amount of activity that went into the city to some power gamma. And you can take a look, for example, a classic source would be Ciccone and Hall's paper in the American Economic Review from 1996. In this case, you need to assume that individual firms are too small to internalize the impact of their output on agglomeration. This is going to change the parameters, but not the basic structure of the labor demand equation. Okay, now we've got the non-traded good or housing. Now, before we had this sort of thing where we're going to put different houses in different places, no. Here, there's just a bunch of housing that's being delivered, bunch of non-traded good that's being delivered, okay? There's going to be 2 things that are going to go into this, capital and the non-traded good. So we're not using labor to create housing. You can, okay? It adds yet another complication, but here you just basically buy the mobile homes from somewhere else and then you dump them down on top of the land. That's what's going on in this. You need land and you need to buy the mobile homes, which are capital, which is coming from somewhere else, okay? The non-traded capital has a fixed supply of MC. The capital is, again, purchasable at R. We can, again, assume in terms of this good that either the two natural assumptions in the case of the AMM model are we're going to have a power function for housing and consumption, which is again going to be a Cobb-Douglas utility function, or each person consumes exactly 1 unit of housing. I don't need to specify that at this point. But typically you need to choose your functions in any of these sort of complex equilibrium things so that they work together, so they marry well with each other. And functions that involve adding don't work well with functions that involve multiplying. So that's part of the problem of having two groups, is when you have two groups, you end up having to add the number of people of the two groups. And that makes things difficult in a model that's otherwise about multiplying. And you've noticed the things that we've had so far, right? This thing is about multiplying, right? Or adding the logs, which is the same thing as multiplying, okay? So that's why the Cobb-Douglas utility function works well with the Cobb-Douglas production function. Cobb-Douglas, of course, is restrictive. If you wanted to assume that local labor produces the housing, you really got to assume Cobb-Douglas. I don't know any other way to do that. It's a beautiful functional form, but ensures that the income elasticities and the price elasticities are 1 and -1 respectively. So you are tying your hands in some ways. Sticking with the height times land, in this case it's h times m, I'm going to continue to use that little h. Here I have the cost of producing is slightly more sophisticated than it was before. Here I've added in a constant term. So if I'm building to, and I've also switched from little h to big H, which is a little bit annoying, I know, for being the height. The cost of building up is h0 times h to the delta c. So we've got a city specific parameter. I'm pretty much going to change that quickly and just make it a universal parameter delta. That's determining how big you're going to build up. And so you're basically going to take your plot of land MC, it's going to be competitively done, and people are going to build up to the point in which prices equal marginal cost of production. In reality, construction costs are actually known. And what happens is going from like 1 story to 5 stories is quite convex. So that delta thing is probably right there. Then 5 stories to 50 is something close to constant returns to scale. And then after 50, it becomes convex again. So it's actually not exactly the smooth power function in reality, but the power function is the easiest thing to work with. And by the way, the RS means thing raises the question of why do people actually build 25-story buildings? Why aren't you coming to this bang, bang, 5 for 50, which is a question probably answered with regulation. I think that housing supply differences across space, which would be captured either by differences in this MC or differences in this delta C parameter, are pretty important for explaining why American cities look the way that they do. So if you think that some cities have a relatively elastic supply, that would mean a sort of, low value of delta, and some would have a high delta, then that would explain why, if you have rising demand, which let's say could come from a higher value of this productivity, this AC, why some places would see more population and some places would see higher prices, which is exactly what you see in the US. So along the x-axis here is the amount of new permitting that went on in the city between 2000 and 2013 divided by the initial housing stock. Along the y-axis is the gap between housing prices and the physical cost of building. As you can see, the places that build a lot aren't expensive, and the places that are expensive don't build a lot, which is most compatible with this type of view that there's heterogeneity in the supply of housing. It's not that there isn't demand for Phoenix or Houston, and it's not that there isn't demand for San Francisco or Los Angeles. There's demand for both places. But in Phoenix and Houston, that demand shows up in elastic supply, and you see a change in quantity. In San Francisco or Los Angeles, it shows up in higher prices because the quantity is more or less fixed. This type of model can get at that, but to do that, you're going to need to have different delta C's, different parameters about how elastic things are. Okay, producer profits are going to be M, that's the amount of land that the individual producer buys, times the amount of profit they earn on each piece of land, which is P sub C times H minus H naught times little h naught times big H to the power delta C. And then that has to be, those profits need to be eaten up by the price of land. And we're not going to worry about the price of land in this model right now. Optimizing is then going to give you an optimal height. This should look remarkably like the optimal height we got in the AMM model. I chose the same function and it's going to deliver exactly the same thing. And it's going to give you a total supply of non-traded capital that is going to be a function of this city-specific amount of land. And of course, the site in terms of land availability and housing supply is Albert Saez's QJE paper on the elasticity of housing supply. And it's going to be a function of the price. So putting this in log terms would mean that the log amount of housing is equal to 1 over delta C minus 1 times log P plus log M. Okay. To work with a system of city-specific equations, we're going to set delta sub C equal to this common delta. Now, we're going to return to microfounding the indirect utility function. So it's pretty simple, but we started with an indirect utility function. Now I just want to assume that you have a utility function where amenities are multiplier times this U. U is going to be come from two different ways, one of which is the same thing we did in AMM, which is one house, one household, one household, one house. So then you just have your utility is theta C times U of YC minus PC. There are times in which that's convenient, but the alternative, but it's not going to be that convenient the way that we set up things here, and it's not going to deliver pretty power functions for us. So there are times when you want to make that assumption, as we did to make things really easy for the AMM model. But since everything else is a power function, I don't want to be subtracting two power functions, which is what goes on in this case. And so instead, I'm going to assume Cobb-Douglas preferences. Cobb-Douglas preferences are defined over traded and non-traded goods, or if you want to just substitute in housing for non-traded goods, that is your right. I will occasionally make the slip myself. The price of the non-traded goods is normalized to 1. That implies an indirect utility function, sigma to the sigma, 1 minus sigma to the 1 minus sigma, theta sub c, y sub c, p sub c to the minus sigma. That's the Cobb-Douglas indirect utility function. You should know it and love it. Now, the thing that's going to be subsumed in one of those big Greek letters is that initial stuff, the sigma to the sigma junk. That's just junk. We don't worry about that. The other ones are going to continue to float around, and that's going to tell you that the log of indirect utility is going to equal to the log of theta amenities plus the log of income minus sigma times the log of the housing price, where the weight of housing price depends on the share of your budget that goes on housing. So the bigger sigma is, the bigger that you have a share on non-traded goods, and that's going to determine how much housing prices impact stuff. Spending in the non-traded good is going to equal sigma times your income. That's the usual feature of Cobb-Douglas utility, that you take your total income and you take a share of its sigma and you spend that on that good. You spend 1 minus sigma on the other goods. Okay, so then you have the total amount of spending on housing, which is PC times this amount of housing. So this PC is the price of housing. You multiply this by the quantity of housing. This has got to equal the total amount spent in the city on housing, which is the number of people times the amount that each person spends on that housing. And remember, L sub C is an endogenous number of workers. So you have 2 equations and 3 unknowns. Housing price is a function of income and labor supply, and income is a function of labor supply. Okay, so you've got log of P is equal to this thing. Again, this big omega is all these nuisance terms. Plus, and again, I'm dropping the C subscripts for the delta, plus delta minus 1 over delta times this weighted average of income, okay, and labor, number of people in the city, and you're subtracting about the supply of land. Adopting the notation, which essentially averages the real productivity parameter and the supply of the non-traded productive capital, we're going to adopt the notation of using ln a tilde equals that weighted average. And then I can just write the labor demand curve as being this productivity minus the number of people. Okay, so these are 2 of your building blocks. They're 2 log equations that are log linear. In this case, we've got income as a function of productivity and labor numbers, and we've got prices, which are a function of income and labor. The third equation is the supply equation for labor that closes the system, the labor supply equation, which is fundamentally coming from the spatial equilibrium assumption. So the old style of this is we just have utility. It's again equal to some Greek parameter times theta c, yc, pc to the minus c. And then, you know, plugging in for this log of the indirect utility gives you this thing, okay? And in a spatial utility model, and in the old style spatial equilibrium, that always has to equal this constant, okay? And that constant gets embedded in the big Greek letter. And so that's going to give us, this is another way of writing it, this represents the relationship between population in the city. So this is the overall equation. This is giving you that population in the city and the utility of its residents. So this, I took all 3 of these equations, I plugged in, and I got utility, which is just a function of productivity, the supply of housing, and you're subtracting off the number of workers. And for this, remember, in this equation over here, I had, I had Y in here, and for this, I plugged in for P. Now I'm going to plug in for Y from this equation over here. And when I plug in both of these, I get this thing. Okay, and so here I have the relationship between the utility and the city and how many people live in the city. And so the comparative statics of this equation are relatively straightforward. Your utility is higher as a function of the amenities. It's higher as a function of productivity. It's higher as a function of the supply of the land that's going into housing, because that's lowering the price of housing, but it's also diminishing the number of people that flow into the city. And so I'm now going to have to take this equation and then solve for the number of people living in the city, okay? Because it's always so this in some sense, if you're fixing the size of the city, you'd be done. If you had a fixed L, you'd be done. And from here, you get utility, which is implied by the size in the city. Of course, we're not fixing the size of the city. The whole point of this is to endogenize the city size. Okay, then in a standard spatial equilibrium model, it allows you to invert that equation. So to go back to it, this is utility equals this weighted sum. The utility has to be everywhere the same. Okay, and so you can just invert everything, and then you get L, which is going to be a function of the other parameters. And that's what we have here. L is going to be a function of productivity, amenities, and housing supply. Okay, it's totally straightforward. Productivity in the city goes up. That's going to pull the labor demand curve up, which is going to pull more people in the city up. Amenities goes up. That's going to raise the utility in the city, and that's going to attract more people into the city, holding the other parameters constant. Higher values of M bar, that's going to lower housing costs, and that's going to pull people into the city. So this model does have some ability to speak to differences in housing supply across the US, but it can't allow a different elasticity. It allows sort of a different stock of available housing supply. This is income. Now you take this L, the way you solve this model is you then take this L and you throw it into the labor demand equation to solve for income. So throwing this thing in, you end up with the income is a function again of the productivity. It's an increasing function because remember delta is greater than 1. So higher levels of productivity means higher income, and it's decreasing in both of the other parameters. It's decreasing both in the amenities and it's decreasing in the supply of housing space. And why is it decreasing those things? Well, higher amenities are a push to labor supply into the city. You're pushing more people into the city, and as you push up the amount of people coming into the city, you're moving along the labor demand curve and wages are going down. So higher amenities mean lower wages. Remember, we saw that at the beginning when we saw that wages were lower in places with nicer climates. Higher levels of housing supply, higher M bar C, more available land, that's also going to pull down wages because you're functionally lowering the cost of housing. That's going to pull people into the city. P sub C, that's the pricing that's going on. That's going to be increasing in labor demand, increasing that A productivity parameter, increasing in theta C, increasing the number of people who want to live in those cities, and it's going to be decreasing in the stock of available space. And so this is giving you sort of core comparative statics. And in fact, one of the things you can do this, and you can see this either in my book on the spatial equilibrium, my Lindahl lectures, or in my lecture that was published as The Rise of the Sun Belt in the Southern Economics Journal maybe 10 years ago, is that you can invert these equations and back out whether or not, what you're seeing in terms of changes in population, income, and price are best understood as changes in amenities, changes in productivity, or changes in land supply. So one of the things that came out of that is even though the Sun Belt is strongly associated with rising population, it turns out that doesn't seem to be associated with rising amenities over time. What's going on is, in fact, the Sun Belt areas, Houston, Dallas, Phoenix, each of which added 1 million people as metro areas between 2000 and 2010. Those are areas which, at least the equations tell you, have radically boosted housing supply over that time period, at least relative to the north. And these are the sort of equations that allow you to invert that. And the way you know that is if you see a place in which populations are going up, wages are not going up by a lot, and prices are going down a lot, that's got to be a shift in housing supply. If you see a place in which prices are which population is not going up, but both prices and incomes are going up, that's got to be something about productivity. And if you see a case in which incomes are going down, population is going up and prices are going up, that's got to be about rising amenities. And that's not what you see in the South. And that's how these equations can basically speak back and forth to cities, is that you can use these to look at the moments of the real data and then infer what must have happened to the forces that are driving urban demand. Okay. It also builds a certain natural logic. So this is the relationship between real wages and city population. This is from largely 20 years ago. And this suggests that higher wages in cities means that, in fact, you've got to have productivity being higher in these areas. But adjusting for cost of living, you don't see any increase, which tells you probably amenities are flat. And that's, again, the kind of thing you can do with this sort of thing, that if you're seeing the same real incomes, you expect to see the same real incomes in places if amenities are the same. This is from 20 years ago. Actually, if you go back 40 years ago, real wages were higher in cities. And if real wages are higher in a city, the spatial equilibrium tells you what must be going on. Amenities must be lower. Remember that from the first thing, and that comes out of these equations as well. You can get real wages here, by the way, if you take the difference between this W and sigma P. So if you multiply this by sigma and subtract it from y, that's how you'll get real wages. Okay, now the new style spatial equilibrium with taste heterogeneity. And this is what you need to be doing in the sort of modern world, is doing probably a fancier version of what I'm giving you. But here we've got taste heterogeneity, you've got type 1 extreme value preferences for particular locations. And again, Rebecca Diamond's job market paper in the AER is a great place to start. Like Leah Platt, she was one of our PhD students. This is the amount of people living in the area. It's this utility weighted average of L for a city. This just means that the labor supply is equal to some set of constants, which are not changing across cities, times rho, which is this variance of the type 1 extreme value term, times the indirect utility. In this case, you want to assume directly that the indirect utility function is the logs already taken. You can always do, it's your model. And then so you plug it in, and this model gives you that ln of L equals this thing, equals rho times this indirect utility function. It's not that different from the standard spatial equilibrium. And that's the beauty of type 1 extreme values. You don't lose everything that you had before, you just have an extra parameter floating around. And that's exactly what we're gonna get here. Okay, so instead of having, went back here, we had this thing, this psi thing here. This parameter was doing this work in these things. This is this function of these different things. Here, you have a thing which is doing exactly the same work, which is this, and this eta thing, I think. And here you have the rho, which is giving you this parameter which reflects the fact, and just look back for it. Rho is determining the extent to which differences in utility impact the number of people that are living there. When rho is really high, then an increase in utility pulls a lot of people in. When rho is really low, then an increase in utility doesn't pull that many people in. And so that's why this rho matters, is it's floating all around here. And you can see actually when rho goes to infinity, you're right back with psi. So if you divide top and bottom by rho and you run rho to infinity, you get back psi again. So in some sense, the old style spatial equilibrium model is a limiting case of the new style spatial equilibrium model. It's a pure generalization. Okay. You then do exactly the same things that you did before. You take this L thing, you solve out for using the three equations. The three equations, again, are the labor demand curve, the building supply curve, or the non-traded goods supply curve, and the spatial equilibrium curve. You then have got three equations, three unknowns. It's all linear once you've taken logs of everything. And so you can invert this thing and you have labor supply, again, which is going to be a function of, size of the city is a function of productivity, amenities, and again, positively in terms of the number of people living in the city. The only thing that's different is now the extent to which these things influence how many people live in the city is mediated by this rho term. It's mediated by this term, which is about how important are the preferences that are place specific. Where would those place specific preferences come from? Well, I don't know. Maybe you like the place that you were born at, and this is capturing those preferences. Maybe you just have a particular taste for Milwaukee. I don't know. But those rhos, that rho parameter enables you to speak about whether or not that the extent to which differences in utility don't immediately lead to infinite numbers of people crowding in. So it creates a break on labor supply, and it just changes the equation slightly. This is ln y. Y is going to be the income, and the income is increasing with productivity and decreasing with amenities and with housing supply, just as it was before. And finally, you have prices. Prices are increasing with productivity, increasing with amenities, and decreasing with M bar C. Now, I don't promise you that I haven't screwed up somewhere in these expressions. I've gone over them a couple of times, but I was doing this late last night. So this may be a little bit off, but the basic structure is entirely right. And of course, the comparative statics are right. So notice that rho mediates some terms and not others. Okay, so this is the term that relates the population elasticity with respect to utility. When it goes to infinity, you recover the old model. Every term in this L equation is moderated by rho because rho is within this eta term. Okay, every term here is moderated by rho. Not every term here is moderated by rho because here you're dividing by rho, and so that's taking the rho out of this thing. Okay, and what's going on with this is that, remember, productivity is going to have a direct impact on wages, even if it doesn't change anyone living in the city. Okay, the big things are unchanged. Productivity boosts prices, population, and income. Amenity boosts prices and population, but lowers income. Housing supply boosts population, but lowers prices and income. So the basic structure works throughout. And you can again invert these equations and figure out you can estimate the parameters using the moments of the data and figure out what you think is changing at the city level or what's different in a cross section as well. And it provides you with a guide for everything else that follows. And while modern urban work has grown sufficiently more sophisticated than this, this basic structure is there underlying, let's say, Rebecca's thesis. One of the things, of course, that Rebecca does that this doesn't do is have rich and poor people. Those models are harder. The only cheat that makes you work stuff is that if rich and poor people consume totally different housing stock, that actually works, but it's not if they're competing for the same type of housing, which of course they are. This becomes much more difficult mathematically. The Cobb-Douglas structure is usually a little bit easier, but still you've got this adding up problem anytime you've got L. The usual thing is to use a constant elasticity of substitution, or CES production function, for grouping together the two different types of labor. Okay, so this is again the highlights, the Rosen-Roback spatial equilibrium model. People choose metropolitan areas and each one delivers a bundle of wages, amenities, and prices. A simple linear model would be that for identical people, wages plus amenities minus prices is constant across the US. That means that amenities can even be measured as prices minus wages. If amenities attract people, then this should predict urban growth. So I'm going to show you the use of this in a little bit of empirical stuff. If happiness tells us something about amenities, so if we want to interpret happiness as not about utility, but about something about amenities, so in these southern areas, people are actually happier, then maybe that tells us something about this as well. So I'm going to show you something from a paper that I did 20 years ago called The Rise of the Consumer City, that was done with Jed Kolko and Albert Saez, that uses this logic, first of all, to infer high and low amenity areas in 1990. So I'm taking the gap between prices and income across metropolitan areas. And again, the logic of the model, and just go back to the core spatial equilibrium assumption here. Utility, right? Utility is, if utility is constant, then if income minus prices are higher, that means amenities must be lower. Okay, or prices minus income are lower. So or you go back to this equation here, right, this is the LNV. If you see this log and this is prices, if this thing is larger, then theta must be lower, okay? So with that logic, we're taking the difference between prices and residualizing for income. And you see those are the places that have the highest residuals. So the model tells you they're the highest amenity places. In the US as of 1990, 9 of them are coastal California, and 1 of them is Honolulu, Hawaii. That seems plausible. And the other places are places that have relatively low values of prices controlling for income, or low predicted amenities. The places that are near New York probably are a little bit misleading, because the incomes are it's a question of which metropolitan area these people are actually working in, and we may be misattributing the incomes. But the other ones look kind of right. Anchorage, Alaska, and Rochester, Minnesota, these places are too cold. Detroit has issues. Midland, Texas is too hot. Trenton makes, the world takes, as its big sign says. So these are all sort of plausible things for getting at different amenities. And then we use this amenity value from 1980, and we just show that higher amenity places are growing more. This is compatible with the view that people are paying more for places that are high amenity over time, or it's compatible with you in our model strictly that high amenity places also have growth in amenities. That's what you'd expect to see. But if it was the high amenity places creating growth in amenities, then what you'd expect to see is actually that this gap between prices and income has actually gotten more negative in the high amenity areas. Another view, by the way, about what's going on in terms of the shifting of America from to places that have higher amenities or places that have the Sun Belt, is that we built our cities around productive advantages, about places with high values of AC. Those productive advantages disappeared over time. We became richer. And so we increasingly remade our urban spaces around places that people wanted to live, rather than places where people wanted to work. And that at least is one explanation of why the variable with the strongest predictive power for metropolitan growth over the 20th century is January temperature. Now, as a New Englander, I may like to believe that shows a lack of character, but de gustibus non est disputandum, as we say. Okay, we can also use this happiness data. So this is happiness across space. I've already shown you this. And this is the relationship between happiness and growth. Now, there are 2 interpretations of this, one of which is that happiness is actually self being determined by growth, and the second of which is that happiness is causing growth. So this happiness data is late, it's coming afterwards. So it may well be that decline is related to unhappiness. So these declining cities are delivering poor values of amenities. We certainly can't rule that out. But it turns out when you look at older data, that the low amenity places, the low happiness places, seemed like they were unhappy first. That if you go back to the surveys that go back to the 70s, or even the Gallup polls from the 1970s, these areas that are sort of deep red and unhappy, and say they're more unhappy now, appear to have been relatively low happiness 60 years ago, and even more low happiness then. And that at least is compatible with the view that historically, a place like Scranton, Pennsylvania, which is this place over here, where my wife's grandfather worked as a coal miner, going into the mines at age 11 and dying of black lung at 59, was a place in which you could actually earn a pretty good wage. But at the same time, it was a fairly low amenity life to go in and out of a coal mine, right? As those coal mine jobs have disappeared, you've moved to places that are, considered to be higher amenities. And so people have rebooted the urban system around higher amenities. And that's at least one interpretation of what's going on here. So I'm done with the AMM. Again, it's a simple structure. Both of them are about spatial equilibria. Both of them pose some form of assumption about it. In the AMM model with heterogeneous taste, it's not literally true the average utility has got to be equal across space, but it is true that the marginal utility has got to be equalized. And that's how the spatial equilibrium plays its way out. But in both cases, we're using this assumption to organize people over space. And in the AMM model, we have two additional equations that give us housing prices and income, one of which is the labor demand curve, which is coming from the free entry of firms and moving along that labor demand curve. The second of which is around the production of non-traded goods. In the case of AMM, we had the production of non-traded goods, the production of housing, which was giving us density, even when people all consumed the same housing unit. We had more density at the city center, not at the city's edge, because the people were willing to pay more for housing, but we didn't have variable wages. And so we just had two types of actors who were moving on. The simplicity of the AMM structure, the lower levels of maximizers, then enabled us to deal with an actual spatial structure. Because as you notice, in the case of these equations, you got these different C's, but I'm not telling you anything about where these C's are. They're just C's that are endowed by their creator with certain inalienable attributes, which are A tilde C, theta C, and M bar C. And those inalienable attributes are determining the location of people, their incomes, and their prices. And with that, thank you for those 1.3 thousand people who seem to be still with us. I appreciate your endurance through this thing. It's an awful long time to watch someone on Zoom. It's an awful long time to speak, but I'm really grateful that you gave me your time today. And I hope you do more urban economics. This has been a wonderful field for me. The study of cities has been a tremendously joyful thing for me to research in my life. And it's filled with people that I deeply admire, which includes everyone who will be speaking in the lectures that are to come and everyone who's on this webinar as well. And I think it's hard to beat a life spent trying to understand the world's cities and to try to teach those cities about themselves in ways that ultimately lead them to be better places. So what questions have you got for us, Fabian?
Ed, thank you so much for a terrific lecture. We have a whole lot of questions. Let's just do 6 minutes of questions and then we have to wrap up. The first one is by Jorge, which is about there's a large literature on the urban wage premium and city-size wage gaps, which suggests that similar workers earn more in larger cities. But in the Rosa-Rohrbach model, wages go down with population, moving along the labor demand curve. What is missing from the Rosa-Rohrbach model to rationalize this? Is it only a generation?
No. That's very helpful because it enables me to explain things. There's no problem. There's nothing compatible. Okay. What this equation means is that higher values of that's not the right equation. The right equation is this one, or even further back. Where should we go? We've got to go here. This equation. So this equation, which is the firm's labor demand curve, says that if I have an exogenous shift in the amount of labor, that wages will go down. So that's exactly right. Okay. If indeed bigger cities were just ones that people were exogenously forced into, then you would expect to see lower levels of income. But if you think that what's defining about big cities is they have a higher value of productivity, in this case, it would be exogenous productivity. So if that A tilde C was higher, then you can easily see that big cities have both higher wages and lots of people. And go back to these solving equations that we got here. So if you have any place that has a higher value of A tilde C, you will expect to see higher population, you will expect to see higher incomes, and you will expect to see higher prices. And that's exactly what we see. This model is completely compatible with the view that big cities have more people and higher wages. Now, what they're not compatible is if you had a labor supply shift, meaning if amenities suddenly went up and the defining characteristic of cities was just they were pleasant, then they should get lower wages. That being said, I do think we're missing agglomeration economies in this model. And I do believe, in fact, that some portion of the urban size productivity premium is not just about, exogenous productivity, it's hard to imagine where that exogenous productivity would come from in the 21st century, right? At one point in time, cities may have been more productive because of things like the deep harbor of New York or the steel or the coal mines that surround Pittsburgh. But now that productivity is likely to be endogenous. And so that's why we have a agglomeration model. So you're exactly right about that. But there is nothing logically inconsistent about this, because the equilibrium equations tell us that we should exactly expect to see large places are more productive if those large places are determined by high levels of A tilde C.
Thank you very much.
Great
There's another
question
here, referencing some earlier work of yours, which is how would you connect the Rosen-Rohrbach model to your work on durable housing and urban decline? And maybe you can briefly,
So the model of durable housing and urban decline is that, in fact, cities build housing and get to an equilibrium forward-looking point. And then when they receive negative shocks, the housing remains. And so cities grow in a way that is compatible with this graph here, but everyone's supply curve of housing is vertical on the downside. And so at least temporarily, the cities lose prices before they lose population. And so you'd expect the process of growth to be fast, as indeed we find. This is Journal of Political Economy, 2005, and the process of shrinking to be slow. So what that calls for is a dynamic Rosen-Rohrbach model, where in fact the supply of housing is downwardly rigid. And so you basically repeat this model over and over again. I like to have the model in which basically the people are reshuffling each time period, but the housing is fixed. And so if the price goes below the new construction cost, you don't add more things. You have a little bit of a problem because the price in both of these models is, at this point in time, since all of these were static models, I was fuzzy about whether or not this was a rent or a price. Once you actually need to get to a model that's dynamic of the form that you suggested that I talk about, you actually need to then think about what the price is that's predicted by this. Okay, so you have to have the price be formed by the expectation of the net present value of future rents. And it's that price that will determine new construction. But this point about vertical supply on the downside is actually quite important for thinking about what COVID will do going forward to cities. If you tell me that some fraction, 15% of the labor force is going to start teleworking, and some number of older Americans are going to want to leave cities because of health risks, I would tell you for most big cities that will show up in price long before it shows up in quantity. Okay, so there's a gap between, you only really lose quantity when people decide in the long run that they want to leave things vacant. And the prices in most of the coastal cities of America are so high above that sort of vacancy cutoff that you expect to see prices go down in San Francisco, especially for commercial, and New York and places that are downwardly hit by this, long before you expect them to see them vacant. Where you expect to see vacancies are places where you're already much closer to this cutoff threshold for actually leaving things open, which is the sort of kinked part of the supply curve. More questions.
Great, Ed. I think we're going to do one last question, and there's one that's, I think, kind of very general, and so it's maybe a nice question to ask for young researchers that are listening to this lecture, which is, how do I choose the right model? Are there features of either model that make it better suited to certain questions, settings? And maybe that question is kind of interesting more generally. How do you choose the right model for the urban question you're studying?
Depends upon what you're trying to do. So AMM is useful mostly for sort of intuition about things. It did serve as a useful empirical benchmark for my paper on where do the poor live in cities, but certainly you're only going to use AMM for choices within city. And you probably only want to use it in a case in which you're not that worried about different neighborhood formations. Notably, there's versions of AMM in which you want to think about them differing not just by travel costs, but other amenities. And if that T of D is interpreted as the difference of amenities between location, then it becomes somewhat more general than this structure. And you can think about the AMM being sort of a within city thing. Alternatively, if you take what I've given you for the other model and turn off the differences in wages, you can think of each one of those C's as just being differences in neighborhoods. So you can think of the Rosen-Rohrbach model as a within city model if you turn off the wage differences. But I would say the main differences are you thinking about within cities or across cities? AMM is a within city model. So if you're trying to explain the microstructure of a city, then you need something like AMM. If you're trying to think about the equilibrium across metropolitan areas, then you need the Rose and Roback model, and they're really meant for different functions, and consequently they have different uses. But again, in all models, you need to figure out the right place between how much complexity you can handle and how much of the world you want to capture. And there's always a trade-off, right, where you want sort of, to capture as much of the world that you can and capture the important aspects, but at the same time, you want to leave yourself with a model that you can work with. And that's true whether or not you can do more with simulations, but there's still limits to that too, okay? And you sort of always have to think about where are the compromises that I'm willing to make in realism, and find the right place to land with that beautiful combination of sort of both enough realism and enough ability to solve and enough parsimony. So with that, again, thank you all. Thank you to the UAE for inviting me to give this lecture. Thank you all for attending. I certainly had fun, and I hope some of you have had fun as well.